DOE CSGF Fellow Christina White in the field of mechanical engineering at Stanford University.
So I'm going to talk a bit about two different projects. The first is the project I was working on prior to COVID-19, and the second is a COVID-19 related project. So I'll spend the first half of the presentation on my research applying machine learning to aerospace problems, and the second part of my presentation on a mobile app for alerting people of their exposure to COVID-19, but anonymously. So the first part of the presentation, I'm going to focus on some neural network architectures that I was looking at for approximating solution to fluid dynamics problems using the kinds of constrained data sets that are more common in industry. So to get started, my background is I worked for a few years at Honeywell Aerospace before coming to school at Stanford to finish my PhD. And while there, we ran into this very typical problem that we see a lot in CSGF, where engineers and scientists are running finite element computations or computational fluid dynamics simulations, and they take a very long time to run. So my goal coming back to Stanford was to find a way to possibly use any of the new developments in machine learning or AI to apply to this problem. What are the methods that are out there? What things are new and might be able to be applied to this problem, and also what we might be able to develop that might be sort of tailor-made for fluid dynamics problems for speeding them up and getting good approximations, even from very limited data sets. So I think that the best current way of approaching the problem is using ROMs. So I was working with Charbel Farhat's research group to compare ROMs to some different neural network solutions. And one of the reasons why you might not want to use ROMs are a few different reasons. One is that they're hard-coded and therefore intrusive. So if someone in industry did want to use ROMs, they would have to take, it would take a long time to kind of get spun up to start using them. You'd have to go into your code and make changes. At CSGF, we might be interested in doing that, but in industry, it's a little bit of a barrier to getting started. So it's one reason why you might not want to use ROMs. So you have to know the model and the governing equations. And also, they don't always work for various reasons. If you have very little data, or for really highly nonlinear problems, the simulation time might not actually improve over the full order model. So there are some reasons why you might not want to use ROMs and instead want to use some other method. So the problem is, how do you use, in industry, you might have very limited data sets because it takes a very long time for simulation to run. However, you may have already run a few simulations. And is there a way to learn from those previous simulations in order to get good predictions, not necessarily to speed up the simulation, which is one path for research, but to get immediate good predictions. And so that's what I've been looking into. And there are a few different ways to do this. One of them is ROMs. You could also just do more basic sort of surface fitting, but that often doesn't work for, again, for highly nonlinear problems, and those are kind of what I focused on here. And so I started looking at neural networks, and I just want to show the results of one particular kind of network, which is the more basic, fully connected network. And the way that I set this up was for a simulation. You might have a lot of data in space and time, and you might have a few different solutions. And so in those solutions, you've maybe varied a few different parameters. And so the idea here is to map those parameters, like space, time, and whatever else you're changing, to whatever function is being output. So for CFD, that might be the state variables, like the velocities or pressures or temperatures. Here I have given Berger's equation solutions. So there's a shock wave moving from left to right across a tube. And on the right, I just have a plot of an overlay in in black of the original solution and this multicolor of the estimates that came out of this network after being trained on a lot of, not just on what's photographed here, but on lots of different simulations, and has to try to fit through all of them. And so this is just an image of one of the solutions that it tried to predict that it got pretty close on, but this is really not good enough for an industry problem, especially for a simple one like Berger's equation. So we really want something very accurate and not something that's going to have these kinds of errors in it. So with a lot of the different, I looked at a lot of different kinds of networks. I looked at LSTMs, variational autoencoders, even tried some graph networks and message passing networks, and none of them really fit well. So they're either tended to underfit or overfit, or like struggled to really solve this kind of problem, because it's not a typical problem because of the fact that most neural networks, they're designed to work with large data sets. So the struggle here is that, I'm working with data sets that may have a lot of points in space and time, but that have very few points in whatever these other factors are that you are varying, that you can generate very few solutions for, which I typically label mu in these plots. So after trying a lot of different kinds of networks and thinking about this problem more, I got a little bit of inspiration from one of my classes and reading about the cortex and these cortical columns that were described in 1978 by Montcastle. So on the left here, I have a picture of the brain and the cortex in the outer layer, and this idea that the brain might separate problems the way that maybe not just seems obvious from looking at these cortical columns, but the brain separates problems is sort of also a little bit intuitively obvious to us, that we break problems into parts in order to solve them more easily. And this, at least in some ways, looks like it could apply well to highly nonlinear fluids problems. So there's this picture of the flow over a bullet on the right. So with a shock wave. And so you can see in this photo, like if you're trying to fit one function to describe this whole flow field, that's not quite the right way to think about it, or that's not, if you look at it, the way that you might remember it later. So the idea here is to break this into parts. So there may be this region that's in front of the shock wave, there may be the region near or around the shock wave or just behind it, and then there's a little bit of a wake. So instead of trying to fit one function through the whole thing, which is kind of what this MLP was doing earlier, to design a network that is going to have a bias towards breaking the problem into parts. So this is the first iteration of that I tried, and I wrote a paper on this in January, got published in AIAA, but I'm also working on a second network that works in a very similar way but isn't quite as complicated to train. But this is the first variation on it. So I'll just kind of talk about it because I think it's a little bit easier to like visualize what's going on than the final network. So in this network, there are both function and context networks. So you want to learn, where should I break the problem into parts? Like I don't want to just have to break the problem into parts, like take certain regions and only train different parts of the network on different regions. That's not an automated process, and it's not going to be very fast. So the idea is that the network's going to figure out where it should have those different functions. So some parts of the networks are training what are the functions in this space, and other parts of the network are, where do I break this up? So the context networks are figuring out, where do I break this up? And the function networks are figuring out the function in those different spots. So the first step for training the network, I would train the function networks to figure out just only train the networks on the points that are closest to your guess. So the way that works is with a typical neural network, you're going to train each part of it on kind of every point. However, with this network, I'm only training, like for example, there's this label on the far left, there's F1, and then there's F2 on the bottom. So let's say that both F1 and F2 output a guess for a given point. I won't be training both of those networks for that point. I'll only train the one for which that is closest. So let's say F1 guesses the value of 1, F2 guesses the value of 3, and the actual answer is 3.2. So then I would pick F2, and only that network would be trained for that point. So after training for a while, then you get some solutions for F1 and F2. If your problem is broken into 2 parts, you could also have more of these if you expect that there will be more than 2 parts of the problem, but this is just to more easily visualize it. I'll just show 2 here. Once that's done, then you train the context network to figure out which of the 2 F1 or F2 to use in a given context. So where do I break up? When does F1 apply and when does F2 apply? And then in the end, you could optionally have a step 3 where you kind of iterate back and forth between the 2 to get something that's sort of more smoothed out. So the cluster network results for Berger's equation were very good. You got like very accurate predictions, even with very few training points. So I may only train 3 or 4 examples, and you start getting not just good fit for those examples, but also good extrapolation and good behavior on interpolating between a couple different examples, which is otherwise very hard to get. So I also tried another test case, which is this shock bubble test case, and similar situation that I tried to train on, where it's given very little data to start with. So it's given a very challenging problem where these parts, these problems all look very different, yet trying to see if it can predict and interpolate well between them and maybe extrapolate a little bit. So predictions, I just want to show the fully connected network guess, which suffers from very similar problems as the Berger's equation guess. Like it's kind of not very smooth and doesn't really fit the shape of the problem as well. And the cluster network guess is a little smoother and generally fits a little bit better. So that's about where I was at when in mid-February, when I started working on a separate project, which was more of an independent project between me and another researcher at the University of Waterloo. So the main focus of the project was to try to find a way to perform something like contact tracing, but is there a way to notify people of their exposure that is either anonymous or that somehow preserves privacy? So the point of the project was to look into various ways to do that, what's even available on your smartphone, and you see if there's a way to have an impact on the virus using a mobile app. So we got started in mid-February and looked into GPS and Bluetooth and MAC address logging and what are the different technologies that are even available on your smartphone for possibly getting the information that might be needed to send alerts. And during that research, we realized that likely the best technology for assessing whether people have been in close contact in a way that is like epidemiologically relevant was to use Bluetooth, because GPS has issues that it can't tell whether 2 people are on the other side of the wall or on different floors of a building, and a lot of transmission takes place indoors, so it matters. Meanwhile, Bluetooth, if you use signal strength as a measure of functional proximity, signal strength goes down between walls and floors, and so you wouldn't get so many false positives and negatives. You're more likely to get the correct assessment of proximity from Bluetooth than from some other technologies like GPS. At the same time, my collaborator that I was working with at Waterloo came up with a way to perform these alerts that was decentralized. So instead of a central authority sending you an alert that you've been exposed, what happens is data is sent to your phone of people who have chosen to alert others, but only on your phone does the computation get performed that checks whether you were exposed or not. So that because that computation is performed locally, if your phone tells you you were exposed, only your phone knows that information and not a central authority. So only at that point where we see the alert, you're the only person who knows that information, and there's no way for anybody else to know. So we got very excited because that was kind of the most anonymous way you could do this sort of intervention. And we expected that, especially in the US, that there wouldn't be very high adoption of this technology, especially if it was something that was privacy infringing. So if anything's going to work, it would be something like this. And we got started building a protocol based on this anonymous way of performing these alerts. So on March 17th, we were the first team in the world to open source this technology. And we built, at the time, it was called the SEN protocol, which was contact event number. So instead of like tracing who is interacting, we were calling them contact events because you're only exchanging numbers when an event has occurred where two phones have been in proximity. So there's no identifying information exchanged. So on March 20th, we published a white paper online on this and developed our SEN protocol. Later got put into a larger TCN protocol, temporary contact number protocol, which was used by a lot of other apps in Germany and in the US. And soon after that, another team in Europe started an open source project on their GitHub as well, with the same kind of technology as the SEN paper from our white paper from the 20th. So three teams in early April, DP3T, PACT, and Google Apple announced that they would build, that they were building similar technology. So sometime around, that was March 10th, and there was a lot at the time of like discussion of this technology in the news, and I'll talk about also what we've done since then and why is it that even if you wanted to download one of these apps, you couldn't right now because of the way that it's kind of been gated in the US. So we developed this protocol. We also at that point after the Google Apple announcement could have kind of just said, okay, we're done with this project, but we also wanted to implement it correctly and to continue to build what we had intended to build into an app. This also is then partly a public health research project. What sort of recommendations do you show in the app? How do you get high adoption? So we've continued to work on these problems. So now our team has about 200 people who are active at any given time, mostly volunteers, but also some nonprofit staff. We formed a nonprofit called COVID Watch. We have about 15 advisors, most of them from Stanford and some from other universities like Waterloo and Washington, UWashington and UCSF and UC-Berkeley. And we have about 200 volunteers, but at any given time, there's about 30 to 50 people who are very active and working on the project, working on the open source project and working on various aspects of this. So when I first started this project, it was because of seeing the column on the far right, which is the China app that was released in mid-February. That was involuntary and made full use of all the surveillance technology that they have in China. And like you have to report your symptoms, and that's legally required. And that was the sort of thing that I was worried about, not necessarily that the same thing would come to the US, but that something like it, or something that there would be pressure to build something that was to stop COVID-19 or to help with COVID-19, but that might not be civil liberties respecting. So there's sort of various other technologies that are kind of in between what was released in China and the technology that we have, which is the one on the far left, which is our Bluetooth only technology, which is the only one that's supported by the ACLU and the EFF, or the only one allowed by them, and then those other protocols like DP3T and PACT and the Google Apple APIs are the same basic technology. So now there are several teams and apps that have been released in the US, but they're more based on GPS or centralized Bluetooth, or other kinds of apps that do collect personally identifying data. GPS is itself personally identifying, because as soon as you get a few points from somebody's GPS trajectory, it's easy to figure out who that person is. So GPS is identifying, Bluetooth itself is not identifying, but if you collect identifying information with it, or if you, instead of exchanging random numbers with Bluetooth, you exchange numbers that are associated with identity and somehow, then that would also be not private. So there's a few apps that were released like that. Singapore released an app like that at the end of March. Australia released one, and France was working on one. And we were surprised. We saw one that was like that in Utah, and another GPS and sort of these semi, not quite private apps that were released across the US in a few different states. I think North Dakota and South Dakota as well. Their apps use GPS. So the problem with that is that if you collect personally identifying information, there's always this risk that you might get hacked, and that data is now in the hands of somebody that didn't intend for it to be in. So we advocate strongly for the anonymous systems that don't collect any personal data at all. And what happens is, if you were to use the Google Apple APIs like we're using, those APIs only generate random numbers rather than having to collect any information about you. And so those numbers are generated from the APIs and used later to route alerts. So the quick version of how that works is what the phone will be doing if you download an app. Every 15 minutes, the number changes that it broadcasts. So what it does is it's sending out a random number, and sometimes it's easier to think of like if it's a random word. So every once in a while, at 1 p.m., your phone might be saying potato, but at 3 p.m. later, it's saying something completely different, like maybe it's blueberry. And then somebody else's phone is walking around, and their phone is also saying random, in this case, words. But in the real app, it's just random numbers instead. So what your phone does is it'll keep a log of everything it ever said. So randomly generating these numbers, and it remembers all the random numbers it said, and it clears that after a while. Because after a couple weeks, it doesn't matter if you had COVID-19, but it was 2 weeks ago, that matters less than if you have it now. So what I heard is also recorded. So if you go around, so what I said might be a very long list, and if you're self-isolating a lot, what you heard might not be very much. Maybe you only had a few interactions, so you have this maybe shorter list of what you heard. Now later, if you were diagnosed with COVID-19, you could choose to use the app to then send the list of words that you heard, or sorry, the list of words that you said. So the list of words that I said over time were potato and blueberry and all these other words. And the other apps will download periodically all the words said by anyone who chose to alert others. So your phone will check and see, okay, did I ever hear the words blueberry or potato? And if it did, then that means that you were exposed. So that's the way that your phone can know that you were exposed without anybody else knowing it. So all phones just sort of download the data that everybody said, but nobody knows who interacted with who, because the list of what you heard is only stored locally on the phone. So in order to accomplish this, you need to build both an app and a verification portal. So one of the downsides of building an anonymous system is that if somebody falsely self-reports, there's no way to know who gave that false report. So in order to prevent false reporting, you also need a verification portal on the public health side. So usually, I think most public health departments will want only people who have tested positive for COVID-19, but let's illustrate the case where you're just diagnosed positive by your doctor. It's possible that some states will allow you to alert others just if your doctor thinks that what you had was COVID-19. So you talk to your doctor says you think diagnosed that you're positive, and you can then choose to alert others using the app. Whoever has access to being able to say that, like your doctor, might log into this verification portal, and that portal generates a random number again that is not associated with your identity. It's a random number, and you type that into your phone, and that just means that it was positive, so that you can report to others that they may have been exposed. So the idea here is that contact tracing works, but it's very hard to do when there are very large numbers of people who might have this virus. So When the numbers are still very low, some number of contact tracers will work, and that will be very effective. But if the numbers are high, like we're seeing right now, it's very hard for manual contact tracers to contact everybody. So the idea with exposure notification is either you're going to be able, it'll work because of the fact that contact tracers won't be able to reach out to everyone, or maybe they will be able to reach out to everyone. And even in the scenario where there's a low number of people that have it, there might be some people who you don't remember when the contact tracer talks to you, running into, maybe it's somebody you didn't know or you were standing next to in line. So a few more people might be alerted that they were exposed than might be alerted via a contact tracer. So another thing that we've thought about with this app is harm reduction versus containment. So a lot of the apps that are out right now will tell you to stay home for 2 weeks if you've been exposed. But the problem with, especially if this is a voluntary system and it's anonymous, people might not decide to stay home for that amount of time, because that's a very long time to stay home, especially if the economy reopens again and people still need to go to work. 14 days is a lot to ask. So so when alerts are sent, we're tailoring it to how long were you actually exposed for, and how long, like how many times did you hear one of those random words for? Like, was it for 15 minutes? Was it for longer? And based on how many of those you heard and what the signal strength was at the time, then you can give some measure of like how likely is it that this person who was exposed might actually have it. And if the risk is very low, then we don't have to ask them to stay home for as long, but that will still help because some of them will actually have it. It's just a low probability. And then if your risk is much higher, then ask those people to stay home for 7 days. So we're hoping that by sort of tailoring that advice, that will make people more likely to actually comply with the advice and more likely to stop the virus, because if you've asked for too much, I think people are less likely to actually do it. And in the case of contact tracing, you can actually identify who those people are, but in the case where it's anonymous and you're not identifying who those people are, then it really depends on people being willing to follow guidelines. So we started doing some research around the Google Apple APIs. So we're the first team in the United States to be piloting this technology. And we're piloting this in Arizona right now and working with the University of Arizona to do studies of Bluetooth attenuation, validating that the app works, and should be piloting on a larger scale for the students who are already at the university in a few weeks. And thank you so much.